Yeah, hi. Good evening, everyone.
Good evening, sir.
Okay, good evening. So, this is the session for quiz season, and this is the second session. So, we will discuss the important questions for quiz 2 from week 7 to week 8. Okay, so today. So, before I have some set of practice question of PYQ, previous year questions, and also we have also released the mock too, so that if before starting, if anyone have any query in mock questions, so you can ask any mock questions related query.
No, sir.
Okay, so all questions are you have solved or discussed in the previous session.
Sir, in previous session, week 5 and week 6 question was discussed.
Okay, and mock questions there is no query, all are solved.
As of from mock only, week 5 and 6 was discussed, and
Okay,
some
okay,
question from their side.
okay, from the assignments. Okay, okay, okay. So one second. Okay, so I have opened mock first. So if anyone have any query from week 7 questions, okay, so week 7 and week 8, then you can ask me. As you mentioned that week 5 and week 6 is already covered. So if I see here, so I think max heap is the week 6, 9 is also week 6. Consider the following element instead of given able tree. Okay, so the 10th question is week 7. Okay, so we will discuss these questions from 10th, and how many we have total? 16, 10 to 16, 7 question. Okay, so I hope you all know about how we creates the AVL tree. So as we have already discussed this process in the weekly live session, but we will also solve that how we will create a AVL tree for this question 10th question. Okay, and what it is asking that which of the following nodes would be leaf nodes in tree. So how this first
Sir,
step
could
is,
you please zoom in?
okay, one second. I think this is fine.
Yes.
Okay. So no problem. I'll use the notepad for this. So let me check in website. Hmm. So I'm just copying this question statement, and I'll explain here. So now let's create a AVL tree for this. So how we create the AVL tree? Generally, this type of questions ask for a small sequence because it takes some time to create the AVL tree. So let's start with this first step, left to right. We will take one element every time, and we will create a binary search tree basically. Okay, so as you know that insertions happen according to the binary search insertion rule, but at any point if we found that unbalance, that we rotate the tree and we make balance. So first node 36. Okay, so 36 will become a root node. So like this is the root node. So there is no node, so we will also calculate the balance factor for each time when we will insert a node. After that we will update the balance factor for the node. So that balance factor for this node is what is the left height and what is the right height. So left height minus right height. So
Zero.
yeah. So what is the absolute value we are getting, that we will note down here. So here zero height is there on the left. That means what is the left subtree? So there is no left subtree and there is no right subtree. So that means zero height is there also. Zero minus zero is the balance factor for this only. Next step is 40. So 36 we have as a root. Now 40 will be added into right. Okay, so 40 is greater than 36. So this 40 will be added here. After that, we will update, we will calculate the valence factor. So for 40, So there is no left subtree, no right subtree. So 0 0 height on the both side. So always you can directly put 0 balance factor on the leaf node if there is no child. So balance factor for this is 0 and balance factor for 36. Now you can see left there is no subtree on the left, so 0 height is there. But there is a right subtree with one node, so that means one height is there. So here height is not a number of nodes. Okay, the height is just a number of nodes in a longest path from the root to any leaf. Okay, so that is the meaning of height. So here this is just a one node in the subtree. So this is the part where we are considering this is a subtree. So this have only one node and there is no height. So no children for this. So that will become a one height subtree. So that means 0 minus 1. So 0 minus 1, we are getting minus 1, but we will take absolute value. So 1 will be the that balance factor for this 6. So still this is balanced because we know that if our balance factor become more than 1, then we consider as a unbalanced. So next 32. So now we have 36 at the root, 40 is the right child. Now 32. So 32 is smaller than 36. So that means the space is available on the left child. So we will add 32 here. So now both are leaf. So balance factor will be 0. And for 36, left subtree height is 1, right subtree height is 1. So 1 minus 1, 0. So still this tree is balanced. Now next is 18. Okay, so 18, 36, and this is the original tree we have. And so 18. So 18 is smaller than 36. Okay, we will always start comparison from the root node. Then we will move. So smaller than 36, we will move to the left side. Left side child is available. So we will again compare. 18 is smaller than 32. So that will be we have to move to the left side and there is no child available. So we will add this 18. Okay. Now balance factor for leaf node is 0, 32. So 32 balance left height is 1, right height is 0. So 1 minus 0, 1. Okay. For 36, now this is the left subtree for this. Okay. And this is the right subtree. So what is the left subtree height? So you can see 32 is the root for left subtree and this 18 is only one path is there from root to leaf. So in this path, two nodes are coming. So we can consider that two height for left subtree, and right subtree height is 1. So 2 minus 1, 1. So still all balance factor value are smaller than 2. So we will consider this as a balanced tree. Now next is 72. So 72. Now we will 36, 32, and 40, 18. Okay, so now 72 is greater than 36, then we will move to the right, greater than 40, then 72 will be insert here. So now balance factor, this is 0, this is 0. So for 32, 1 minus 0, 1, and 40, 0 minus 1, minus 1, we will consider as absolute value 1. And for 36, 2 is the left height, 2 is the right height. So 2 minus 2, 0. So still it is balanced. So there is no rotation required till this point. Now next is 5. So we will add here 36, 32, 18. Okay, and this 40 and 72. So now 5 is smaller than 36, is smaller than 32, is smaller than 18. So we will move this on this path and this will be added here. So leaf node balance factor is 0. So we need to only update the balance factor from the new node inserted position to the root node. Okay, so other side the balance factor will remain same. Okay, so like 72, 40, this will not be affected by this 5 insertion because this is happen on the left subtree. So we can directly put 0 and 1 here, so that is will remain same. So 5 and 18 balance factor will become left height is 1 and 0, 1 minus 0, 1. 32, 2 height is the for the left subtree and right height is 0. 2 minus 0, 2. Okay, and for 36, 3. on the left and 2 on the right. So 3 minus 2, 1. So now you can see we are getting more than one height on one node. So this part. Okay. So this is now become a unbalanced, this node. So we will make this as a balance. So this is the condition of left rotations. So you can see balance factor is become 2 on this 32 node. Now which side height is greater? Left side. And after moving to the left child, which side height is more? Left side. Okay, so L type of condition is there. So in this situation we apply clockwise rotation by just pointing this as a pivot node. Okay, pivot position. So just pull this onto this side. So 18 will become a 18 will reach at this 32 position. 32 will become a right child, and 5 will also shift at 18 position. So after rotation of this part, so our tree will look like this. So 36, 40, and 72. This is will remain same. But here 18 will come at this position, and 32 will become right. So 32 and 5. Okay, so this is the way we apply the rotation according to the condition. So now the balance, after applying the rotation, only one rotation is required for this type of situation. So 0 balance factor for this, 0 is this, 0 for this. Now 18. So 1 minus 1, 0. For 40, this will remain same. For 36, you can see where we have two paths. So like 36, 18, 5, this is the one path from root to leaf. Another is 36, 18, 32. So on both paths, we have the number of nodes. So on this part actually, not from the 36. This is the left subtree. So 18 to 32, 18 to 5, both have the two nodes in the path. So 2 height is there on the left, 2 height is on the right. So 2 minus 2, 0. So now you can see all balance factor is now become less than 2. So this become a balance. So now 5 is done. Now we will add next 35. So 36, and also this insertion is also important for binary search questions, binary search tree questions. Okay, so sometimes this similar type of question asks for binary search. This is the sequence: create a binary search tree and ask what are the leaf node. Okay, so this insertion operation should be very clear. 40 and 72, 18 and 32. This is the current tree we have. Now we are adding 35. So 35 is smaller than 36. Now 18 greater than 36, also greater than 18. Now we will move to the right. So greater than 32. Yes. Okay. So 35 will insert here. Okay. So now just again count balance factor. So this is now 0, 0, 0, and or this will become 1. Now 32. So 0 minus 1, 1. Okay. For 18, 1 minus 2. Again, this is also 1. For 36, 3. 3 is the longest path. Okay. So 18, 32, 35. This is the longest path in this. So 3 nodes are coming. So 3 height is on the left and 2 height is on the right. So 3 minus 2 is now again 1. So you can see this is also a balance. Now next is 34. So 34, so 36, 18, 5, 32, and 35, and this 40 and 72. So now we are adding 34. Okay, so 34. So 34 is smaller than 36. Move to the left, greater than 18. Move to the right, greater than 32. Move to the right, smaller than 35. So 34 will insert here. Okay, in this place. So now balance factor 0, 0, 0 for leaf. Then for 35, 1 minus 0, 1. For 32. So 32 is right height. Right height is now 2, left height is 0. So 0 minus 2, 2. This become a 2. 18. So 18 left height is 1, right height is 3. Okay, so this is the complete one path where three nodes are coming from 32 to 34. So 3. So 1 minus 3 again here 2. Okay, for 36. So this is one. So 36 is what is the height for left subtree? 1, 2, 3, 4. Okay, so 18, 32, 35, 34. This is the longest path for this left subtree. Right subtree we have only 2. So 4 minus 2, 2. So in this situation, you are getting multiple nodes which have greater than one balance factor. So in this case, always solve the lower one first. Okay, so this part. So once you will make this part as a balance, so above that balance factor will also be reduced because that is also depends on the lower one. So this part is what type of condition is this? So 32.
RL.
RL.
R. Okay. So yeah, which side height is greater from 32? So that is right side.
Right.
And moving to the right child, which side height is greater? Left side. Okay. So RL. This is the RL condition. In this case, we apply two rotations. So first rotation apply on the child node. Okay. Of this balance factor 2 node. So this is the clockwise rotation. Okay. On this 35 position. And after applying this one rotation, second rotation will be performed. So this is the first rotation. Okay, so first rotation is this, and second rotation will be apply on this 32. That is the anti-clockwise rotation. Okay, so two rotations we requires here.
So,
So huh.
can you again explain that why clockwise first?
This is the rule for this ABLT. If we are getting this RL type of situation, so in this case we apply two rotations. First rotation will be applied on the child node of the node which have variance factor more than one. Okay, this so this one. So that rotation we will apply on this 35 node. So after rotation, so we will get like this. So 72 and 18 all will remain same 5. Yeah. So first rotation we will apply here like this. Okay. So this 35 will become a right child and 34 will move at 35 position. So that means 32 will remain same, but here this 34 will come and 35 will become like this. Okay. So we have made this one rotation. So after getting one rotation, we are getting this type of things. Okay. Still this is not balanced. Now, second rotation we will apply on this node, that is anti-clockwise. Now this, so you can see this become a RR type of condition. Okay, RR type of rotation we apply anti-clockwise rotation on this node. So after that 36, we are getting 40, 72, and 18 and 5. Okay, so this 34 will reach at this 32 position and 32 will become a left child of this 34. So 34 and this become a 32 and this is 35. So now this after two rotation we will get this. So the situation if you are getting LL only one clockwise rotation is required. If you are getting RR situation only anti-clockwise rotation is required. But if you are getting LR or RL then two rotations are required. So these are the four type of rotations we apply in the ABL tree. So now finally we are getting this tree. Okay, so now balance factor you can see 0, 0, 0, 0 all leave, and 34 1 minus 1 0, for 18 1 and right side height is 2. Okay, longest path is only 2. So 1 minus 2 1, and this 40 is 1, 36 3. Okay, so left height is 3, right height is 2. So 3 minus 2 1. So you
Wow.
can see all become less than 2. So the above one is also resolved. So now this is the final AVL tree. Now you can see what are the nodes which are coming on the leaf. So that 5, 32, 35, and 72. These four nodes are coming at the leaf. So now this will become a answer for this. Okay, so 5, 32, and 35 and 72. So 35 and 72. Yeah, someone pasted. By necessity to locate the number 43. One sec. I think Prashant have pasted some question. Hmm. So is this mentioned in mock, or you are asking from any PYQ?
PYQ, sir.
Okay.
It is
So this type
uh,
of PYQ you posted on the forum also, because
after discussion. Can you solve this? Because I have seen this the TSS and is plan. So,
uh-huh. Okay. Uh-huh. So this is your question. Okay. So here what is given here, a binary search tree is used to locate the number 43. Okay. Which of the following probe sequence of compared elements from the root to 43 is not possible? Okay. So option one is, so this will be definitely solved by options actually. So first option we have 2, 3, 50, 40, and 60 and 43. So now sequence, because we are what we are looking 43. Okay, these elements. So definitely, if we are starting from root node, so that means first node is the root node. So this is the 2. Okay. Now the second node, definitely, because 43 is greater than 2, so we will move to the right side only. Okay. So this 3 is coming on the right side, greater than, so that is possible. Now 50 is coming, so 50 is also coming on the right side, so that is also possible. Now 40. Okay. So 2, 3, 50. Okay, so next is 40. So 40 is will come here. So 40 is fine. Huh, okay, so now you can see if this is also possible. Okay, because the 40 is still smaller than 50 but greater than 3 and greater than 2. So that all are coming on the right side. So this 40 is coming on the right side. This is also possible. But after 40, 60 are coming. Okay, so 60 element coming. So that means in this probe 60 cannot be come, because this 60 is connect will be connect to the 40 right side of the 40, but 40 is already connected to the left side, so this is violation of the binary search. So this 60 cannot be come on the left side of this 50 part, because this is greater than. Okay, so this probe sequence
so
is not
why
possible.
so why it is not the right side of 50? Because it is greater than the
No,
50.
we are just looking the probe sequence. Probe sequence means we are moving from root to uh, this 43. So that means if any binary search tree. So suppose if any binary search tree we have like 20, okay, and 10, okay, 5 and like 55, 70. Okay, so like this binary search tree is there. So probe sequence means if you are searching like 55, so how you will come reached at this 55? So you will traverse this path. 20 you will compare from this, then you will move to the right side because 55 is greater than this. Then you will traverse this because oh no, so this is wrong. Sorry, uh, 45. This is and suppose this is like 30. Huh. Okay, we are searching 45. So 45 is greater than 20, you will move to the right side. Okay, now 45 is smaller than 50. So then you will move to this side. Okay, now 45 is greater than this 40. So you will move to the right side. So in binary search tree, you are following this sequence of comparison. So like 20, 50, and 40 and 45. Okay, so this sequence is given here and we are validating that. So in this sequence, so what sequence we are validating? This one first. Okay, so we are validating. So 2, 3, 50 we are connecting. Okay, so 50, after 50, 40 is coming. So 40 will come on the left side of this 50. Okay, because this is smaller. But after 40, 60 is coming. So 60 definitely will be connect on the right side of, because it is greater than 40. But now this is the violation of the above one, because according to the binary search tree, right child should be greater than to the current node, and also right sub nodes in the right subtree also should be greater than to the current node or parent node, like this. Okay, so that is the binary search tree rule. So here this is the violation, because 60 is now connected to on this left side part of 50, but this 60 is greater than, this cannot be come in this side. Okay, so because
Okay,
of
sir.
that, this is wrong. And another is like option 61, 52, 14, 17, and 40, 43, and only this. Okay, so here this is starting from 61 root. Okay, 61 is a root. Now 52 will come this side. Okay, so and 14 will come on this side. Now 17 will this side. Okay, now 40. So 40 is greater than this. So this is 40. Now 43. So 43 will come here. Yeah, this is possible. Now you can see if we are generating the path according to the binary search tree. So all are validating the binary search rule here. 50, all nodes are smaller than 61, correct? If you look from the 52, all nodes are smaller than 52. If you look from 14, now all these nodes are greater than 14. If you look from 13, all these are greater than and coming on the right. So all actually are following the binary search. So this is the possible one. Okay, second option is possible option. Similarly, you can validate others. Okay, so just first create the path. Okay, from root to leaf node of till 43 value according to the binary search tree, and then validate that each value which are coming on the left side, which are all values are smaller than to the parent node. Not okay.
Okay, thank you, sir.
So yeah, this we have done. Now Huffman, this next question: which of the following statement is a true about Huffman code algorithm? So Huffman code algorithm, you know that how we create the Huffman code. We select the smaller frequency first, and then we create. Okay. So in this case, smaller frequency will always be come at the higher depth from the root. Okay. So because we are selecting, suppose we have to this type of frequency, like 2 2 and 2 3 and 10 20 and like 60. Okay, so what is the steps we perform to generate the Hookman? So that we select two smaller first, so this 2 will become a leaf node, and 3, and then we combine this and we will make 5 is the addition of this. After that, the remaining one is 5 10 26 60. So 5 and 10 will be select, so this 10 will come here and this will be combined, so like 15. Okay, and then this 15 will be add with 20, so 20, and this will combine like 35, and 35 will be add with 60, so this will combine like, okay, so 95. So this is the process of Hoffman tree. So here you can see that which frequency are smaller, which at that frequency nodes are coming at the higher depth. Okay, in this tree, which has the frequency smaller, which that are coming on the lower depth from the root. So that is the one observation from the process. So here you can see the first option: in a optimal movement tree, if leaf labeled x is depth smaller, then leaf level y. Okay, so that means depth x is smaller, so that means the value of x is, frequency of x is higher. Okay, so this option is, I think, not correct. Okay, so this is the invalid answer, because if x is at smaller depth, like suppose this is the x 60, so this have the smaller depth, and bigger depth, suppose this is the y. Okay, so bigger depth is coming at the higher depth, so frequency of x is smaller than frequency of y. This is not true. Opposite, frequency x should be greater than to the frequency of y. So this option is not true. Huffman algorithm always generate prefix code. Yeah, this is the property of Huffman codes. If you are generating Huffman codes, so each code will be the prefix code. Each code cannot be the prefix of another code. This is the meaning of this actually. So Huffman code, what is this? So this is 0 0 0 0 and 1 1 1. So if you generate the Huffman code for, so the 2 will become a 0 0 0 0. Okay, and 3 will become a this 0 0 0, and this 10 will become 0 0 1, and this 20 will become 0 1, and this is the 1. So now you can see any code is now not a prefix of any other code. So if you just pick this one, this is not coming as a prefix of any other codes. Similar this. So any code cannot become as a prefix code. So this is the property of the Huffman codes, and because of that, we generally say that this code always generate prefix codes. So this option is correct. Huffman code algorithms is based on greedy approach. Yes, so that we have already seen in the lecture. So this is a greedy approach because every steps we are selecting the smaller one and we are generating. So this two and third. So these options are correct for this. Okay. So this is the next. Let me remove this. Hmm. Okay. So this is the another question. So this is also a greedy algorithm based. We have already seen this minimize the maximum lateness problem. Okay. So here these frequent time required is given, deadline is given, and what is it is asking? Okay. So this formula is also given for the lateness. So time of completion is greater than deadline. Okay, so then we will just find out the lateness equal to time of completion minus deadline. Otherwise, zero. Okay. If our completion time is before the deadline, so we will consider the lateness zero. But if it is the after the deadline, so we will just subtract that time of completion minus deadline. So this is the lateness, and we are finding out the maximum of all lateness, all activity lateness value, and that should be the minimum. Okay, because here manager goal is to minimize this problem. So this is the problem which is already covered in the lecture. So here, how we solve this? Anyone can remember how we solve this?
We arrange the deadline according to.
Okay. Yeah. So we arrange this all jobs based on the deadline value in increasing order. Okay. So that means our jobs, this jobs will be select first. Okay, because this have the smallest deadline. This is the second one. Okay. Then third, then fourth, then fifth, and then sixth. So this would be the order to select, and we will start from zero time. So let's we start from zero activity, 0 time. Hmm. And after that we will select this first actually. Okay, this first selected 6 and it takes 2 times, so 0 to 2, this is the time to complete for this. And what is the deadline for this is 5. So that means lateness is become 0. Okay, because we have completed before that. Now next activity will start from at 2 times. So which one? This ID. Okay, so add this time in this 2 or plus 4 6. Okay, so this is 2 and this is 4. So now this is the end point, and deadline was 6. Okay, so at the correct time, so this is also a 0. Now next activity will start this second one. So 2 is required, so 6 plus 2 8. So this one, so 8, what is the deadline for this is 7. So 8 minus 7 1. Okay, so 8 minus 7 is 1. Now next is this one third. Okay, so time is only 1 9. Okay, and deadline is 8, but we are completing at 9. Again 9 minus 8 1. And next is this 12. So 4 times, so 9 plus 4 13. Okay, and deadline is 12. So 13 minus 12 again 1. And next is 3. Okay, so this 13 plus 3 16. So this is deadline is 14. So 16 minus 14 2. So we got all the lateness, and what is the maximum value among all these two? This one. Okay, so and this is the answer to this. Hmm. So this is answer. And the next question is also based on this. So which of the following greedy strategy would always work correctly for the given problem scenario? So we have already seen that how we are selecting. So that always choose the job first, which required time is minimum. So this is not correct. So deadline is earliest. Okay. So how we solve this based on this, whose deadline is earliest. So this is the related question. Now 14th one, in an array two elements AI and AJ forms an inversion pair. Okay, so inversion pair is there. The maximum number of inversion pair possible in an integer array A is of size 20 is. So this is simple formula based question. Can anyone tell me what is the formula we will use here?
N into n minus 1 by 2.
Yes. So that is just so maximum inversion we found if our order is totally reverse. Okay. So suppose if we have element like this 5, 4, 3, 2, 1. Okay. So suppose this is the order, and we are looking the inversion. So how many inversions we are getting? So you can see 5 is making in 4 inversion. Okay, with 4, 3, 2, 1. So that means 4, and 4 is making inversion with this these three elements. So 3, and 3 is making inversion with this two element 2 or 1. So this is 2, and this is making that 1. Okay, so this is 1. So we are adding all these number 4 plus 3 7 plus 2 9 and 10. Okay, and this can be solved 5 into 4 divided by 2. So we are getting 10 directly. Okay, and into n minus 1. So these we are getting. So same formula you can apply here. So 20 into 19 divided by 2. So this is 10, and this become a 190. Okay, so you can directly put this. Other type of question may also ask like this sequence is given, and you have to identify how many inversions are there. Okay, and some previous terms, some inversions. So this is simple inversion pair definition. Okay, but sometimes in previous terms questions, some different definition is given for inversion. So like AI is greater than 2 into AJ. So that in that case you have to check that condition also to find out the inversion pair. Okay, so this is the 14th. So next is this MOM. So as you know that here this MOM is working as a block of 7 elements. So I think in lecture we have covered with 5 elements. So what is the median value according to this function? So this function we have already seen in the lecture. So how we will simply apply the dry run, and this is simple actually. How this is working we know. So just select the block of 7 element. Okay, so this 1 2 3 4 5 6 7. Okay, this is the first block, and second block is now 6 1 2 3 4 5 6 7. This is second, and 1 2 3 4 5 6 7. This one, and 1 2 3 4 5 6. So this is the last one. So 7 element we are picking, and then we will arrange into a sorted order. So 9, this first block 9 7 10. This one.
Sir, why we are taking 6 elements?
No, we are taking we are selecting 7 7, not the 6. So last we have only remaining 6, so we are picking 6.
Okay, sir.
Okay. So here it is given. So median with block of 7 elements. So we are making the block with 7 elements, and after that we will sort each block. So we can write like this. So 3, 3 4 and 5, then 7 9 10 and 13. So this is the first block sort after sorting. Second block is 1 2, and then 6 8, 12, and then 15, and then 19. Okay, this is the second block. And next is so which one is this? 14, mm, 2 10
18,
18,
18,
huh,
21,
21,
24,
23,
3,
23, 25,
4,
24,
4,
25.
25.
Yes. Hmm. And next we have only 6, so we will make 6. So 11, and then 17 17. Okay, and then 20 26 27. Okay, so median element we will select. So in these three we will select like this. How we are picking this median? floor division by 2. Okay, so that what is the length of this 6? And okay, so and 6, length of x 6, and 6 division by 2 3, so 0 1 2 3. So this is will become okay. So now these median are coming, so 7 8 21 and 20. Again we will sorted this, so 7 8 20 and 21. Now what is the median of this? So
Sir,
4 by 2.
26, fourth place, no?
Here, oh, 0 1 2 3, this will come, no? Total 6 element we have. 6 floor
Yes.
division by 2 3, so 3 this will 20 will pick.
Okay, sir. We are starting from zero.
Every we, because we are creating a list every in the block, so every index will start from 0. And here we have 4, so 4 divided by 2, so 0 1 2 3, so this 20 will pick. So 20, this MOM algorithm will return this 20 as a median element from this unsorted. Okay, so this is the one. And next is 16th. Okay, so this is just give me a minute. Sorry. Okay, so here we have the recurrence relation, and we have already seen in the B8, okay, how we can solve the recurrence relation. We can create a recurrence tree first, and then we can observe how our steps are increasing or decreasing, and based on that, we can decide the complexity. So first recurrence relation, we have hmm, so 9 tn equal to 9 tn by 3 plus n. Okay, so we can write like this. So tn we have starting, and this is repeating 9 times. That means 9 time calls are there. So every calls have n by 3 like this. Okay, and apart from that we have an additional step n. Okay, so that first step. Now these are the 9 call. Okay, so if we are passing n input, additional steps are required n. If we are passing n by 3, so that means n by 3 steps are required. Okay, as a this one. So n by 3 into 9 times. Okay, so each call, so this call will take n by 3 as a additional step. Second call will also take this. So that means at this level, 9 into n by 3 steps required. So this will become a 3n. Okay, next level, each call have 9 call. Okay, so now 9 into 9 81. So now the what will be the input for that? So n by 3 by 3, that means n by 9. Okay, so n by 9, this in steps are required 81 times. So 81 into n by 3, sorry 9. Okay, so 9 9 this 81, so this we can write like 3 square n. Okay, so same way this will increase like this. So 3 3 and next level. So the first steps was this, second this is become 3 and this 3 square and this 3 this one. So now you can see these steps are increasing. Okay, so that is the that this is the one type we are getting the increasing way. So how we calculate the frequency complexity for that? So that tn equal to, we consider that uh, that is I think n into log cr. Okay, so where c is the this part. Okay, so division part, so that one. Okay, r is the recursive number of calls, 9. Okay, so we will put into this, so n, or this n we are getting is like as a fn. Okay, so what fn we have? So we have that n. So that log c, so log c value is 3, r value is 9. Okay, so this 9, so 9 we can also write 3 to the power 2. Okay, so now this 2 will come at the and this will become n square, and log 3, log base 3 and 3 will become 1. So that will become a final one, n square. So n square complexity is for this first. And second, we have this 4t. So this is the another case. Okay, we are not. Okay, 4t n by 4 and n square. So let's move to the next. So this is now tn. Additional steps are required for n square. And the next steps we have 4 call. Okay, and tn by 4 each. Okay, that means 4 into n by 4. So how many we are getting? So that is now 1 second. So 4 n by 4. Huh? Okay, so this will become n. And next will become 4 each. Okay, so total 16. And this will also become n by 16. So n by 16. Okay, no, no, no. I'm doing something wrong. Okay, yeah. So this is actually not correct. So n by 4. Okay, so this, if our input is n, okay, so then we are getting n square. And if our n input is n by 4, so this will become a n square by 4 into 4, 4 square. Okay, for each. And that is multiplied by 4. So in this way, this will become like this. So 4 n square by 4. Okay, like this. And next step, each call will use this input n by 16, and this call till 16 call. Okay, for 4 for each. So 16, and we will write like this. So n square by 16 into 16, and this is times 16 times. So 116, and we will write like this, n square by 16. So you can see how what or pattern we are getting. So initially it was n square, then we divided by 4, then we divided by 4 square. Then, so it will increase like this. Okay, so this time we can also write like n square by 4 to square. This like, okay. So this is reducing. This pattern is reducing. So in the case of reducing, we directly write fn as a complexity. So tn equal to fn. So what fn value we have? We have n square. So n square will be the complexity for this. So for this, you can see we are getting this second option. N square we are getting for the first, and n square we are getting for the second one. Okay, so this B option will be the correct one.
Sir, can you
Okay,
do this with previous formula? Means n
which
of
one?
log, n of log n k.
No, no, that formula will not be applicable for this, because here this is reducing.
Okay.
Okay, if we are getting increasing order, so then we use the fn and that log cr, this way, these things. Okay,
Okay, sir.
so this is apply if our order are increasing. If our order are decreasing, we will directly use fn as a complexity. If our order are remain constant, so at that time our complexity will remain fn into log n. This. Okay, so these three steps are there in this recurrence tree. Okay, calculation. So you can just see, you can just look the week 8 slides, and last topic is this, and where these all conditions are mentioned.
Okay, sir.
Okay, so this is the one, and so all these are the mock questions. I have one additional slides where we have more question. So let's move to this. You can also copy this and you can open this. Okay, so you will also get a sample for this. Those who
Sir,
will uh-huh.
sir, could you solve one more question I have given in the chat? It is based on Hoffman
Mm-hmm.
coding. I am getting the wrong answers.
So there is a chance of wrong answer in the previous QPs. Okay, so what answer you are getting for this? I think this is 16 or 17 something.
No, no. This is this not. I am.
Hmm.
Yes, yes, yes.
How many bits you are
I am
getting?
getting the 16, 16.
Huh. So I remember one of the terms where we got two possible answer for this actually. So let me check for this. So we have total 80. So A, B, C, D, E, F. So 80 and 60, 50, 40, and 30 and 20. Okay, this one. So first step we will pick these. Okay, so E and F, 30 and 20, and this will become a 50. Now next step, yeah. Here, okay. Yeah, Vivek, can you turn off your mic? Okay. So now the 50 we have, and so which one we will select? Either we can select 40 and this 50, okay, or we can select this 40 with this one. So because of that, two answers are possible for this. Okay, so if you are getting 16, so that is also possible because what we can do, because we are getting 50 here. So that is the combination of this. So now what are the two smallest ones? So 40 and one of the 50. So suppose if you are picking this one, you will get a 16 answer. So that will start from the bottom up actually. So like 40 for D and 50 for C. Okay, so this is C, 40 and this is 50. Now you will get it this 90. Okay. Now this 50 will be added with this 60. Okay. These are the two smallest. So you will get it like this 60. This is for B. Then you will get 110. And now 80 will add with this. Okay. So 80, this is for B. Oh, sorry. A. Okay, so this will get 90 to 170, and this will combine both. Okay, so this will come to 80. So in this way, how many bits you are getting? So for each length you can count. So one, two, three. So for this E3, and for F is also 3, and for this 1, 2. So this is 2, and 3, 3, and 2 again. So 3, 3, and 2. So total 12 and 4, 16. 16 we are getting. Okay. But another answer is possible if you made, if you select after this 30 and 20, if you select this 40 with 50. Okay. In that case, you will get a one more for this 17. So that is also a correct answer. So I remember this question. We got give the marks for both 16 and 17. Okay. Yeah. So let's move to this. Hmm. So this is the one peer deck. Okay, so you can open this side and you will also get all these access of the questions. So I am also sending the link in chat. Okay, directly open. Okay, so those who will actually participate will also get this PDF as a PDF, all the questions in your mail or something. So I hope you have opened this. I have already sent the link in chat. Not sent? Yes.
Yes, sir.
Okay. So I'm closing this, and let's move to this. Huh. So again, the questions we have, I think 18, 19 question in this. So this is the one question of binary search tree. Someone is pasting something. Okay. So you have this binary search tree where the values are not given, but it is mentioned that these labels are replaced with the values, and all labels are actually following the binary search tree structure. Now the letter indicate the names of the node, not the value that are stored. And what is the predecessor node in terms of value of the node M? So here this M node, we are just looking for what is the predecessor node in the terms of value. So value means if we find out the order, actually suppose these are the values, so we can write these value in increasing order. Okay, Okay, suppose we are getting like 1 2 3 4 5 6, this way, or this m value is representing 5. So what is the just predecessor in the terms of value is this 4. Okay, so but we need to identify in this tree, so what will be the predecessor for this. So how you can solve this?
First in order.
Okay, so you are mentioning in order traversal.
Yes, sir.
Yeah, that is also a correct way. You can apply a in order traversal on this tree, Banisa's tree. This traversal will provide you a sorted sequence in increasing order. Okay, because this in order traversal will read the value from the leftmost value. Okay, left, then print, then move to the right. So in this way, if you know that how in order traversal works, you can apply the in order traversal and you will get a like sequence in increasing order. And at that time you can see which place m is coming, just return the that one previous adjacent node as a answer for this.
C, sir.
C.
Yes, sir.
Okay. Huh. Otherwise, if you have good practice on the binary search tree type of question, so definitely you can observe what will be the predecessor value for this. So because if you just look this m, this is coming of the left side of this g. Okay, so that means this g value, this m value is smaller than this g. Okay, and this g value is greater than this c. So which one will be the closure? So in this type of structure, suppose and this, if m is connected on the left side, so definitely this will be lesser than this 50. So in between, but it is coming on the right of this 40. So that means this value definitely will greater than 40 and smaller than 50 in this range. So which value will be the closure for this? Suppose this value is like 45. So what are the predecessor values? Definitely this one. Okay, but for the more safer side, just apply the in order traversal. That will be the easiest one. So I hope you know that how we find out the in order sequence. So according to the in order, first we traverse the left child, then second step is we print the current node, and third step is we traverse the right child. Okay, so that recursive way. So we can write like this: left recursive call and print the current node, and right recursive call. Okay, in these three steps we perform this traversal. So first step is left recursive call. So just move to the left child. This step is now LPR. Okay, then again left recursive call, first step of this. Okay, if you know the recursion way of the execution. Okay, so we call the new function, and that function that execute again. Okay, so the first step of this call is again left recursive call. We have the left child, so then means we will reach at this PR. First step of this left recursive call, again we have the left child, so we will reach here LPR. Okay, now no left recursive call, so this step is completed, because if there is no left we will not perform anything. Second step will perform at this node first. Okay, so h will be print. Now right. Okay, third step, right recursive, no right child. So all three steps are complete. We will return back to the call for this. Okay, so this is the left child. This part is now done. Second step is print current node. So print this is t. Now right recursive call. So right is there. So all three steps will be apply here. Now left, move to the left here. No left, then print this node. So this O, and then no right. Now right recursive, print current node I, and right recursive call. So LPR. So these steps, left recursive call is not there. Print current node. So this is P, and no right recursive. All three complete, move back. All three completed, move back. So all three completed. Now move back on this. Now left is complete. Print current node. So B and right recursive call. So right is here. Left. Okay, so first step is left. So in this way you can apply your algorithm in only these three steps. So No left recursive print J, and uh, print no right, here print E. So right is there, so LPR. So no left, print this node K. Okay, right is complete. So all complete. This one also complete. Move back here. This one done. A. Okay, so A will come here. Right recursive call. So LPR. No left, left, LPR. Okay, so this L will print. Now F will print. Okay, no right, and then C will print. And after C, you can see here LPR, and then this side LPR. So left is M. Now we got the answer. Okay, so after that we reached at this point. So what value is just coming before this? That is the predecessor value, because this order is actually a sorted order in terms of value. So we are getting C just before M. So this is the predecessor. So we can return this as a answer. Okay, so you can apply in order traversal in this way. And we have also discussed this all three order in lectures. You can go. So in predecessor, pre-order, we follow the step like first left traversal, then right. No, sorry, print step first, then left, then right recursive call. Okay, post order, we follow the steps: left recursive call, then right recursive call, and then print current node. This is the only change in these. Okay, so how many of you see? Okay, only 5 have marked. So others are also, please try to solve these questions. So there is chance maybe some question will come as a similar type of in your exam. Okay. So let's move to the next question. Okay. Which of the following order will be printed by the given code snippet? So in this slides, actually, we have now I have removed the options from some questions. So you can just actually calculate that. Okay, so here just see how the traverse implementation is there. So traverse implementation, which or type of order we are following for this? Okay, this one. So this is the now traverse left first. So that means left step is the first, right step is the second, LR, and this is the value. So print step. So this is a post order traversal. Okay, post order traversal I apply on this. So that this is LRP. So that left LRP, that left first LRP. Okay, so no left, no right. PD is the first one, and then here no right is there, LRP, and the left is there, LRP. So H will come next. Okay, you complete. Now no right, print E. Okay, and this print B. Now L is completed. Okay, now right part. So LRP. Okay, now left, LRP, left, LRP. No left, no right, print I. Okay, no right, print F. Right is there, LRP. No left, no right, G will print. And now we will move back. So this with C will print. Move back, now A will print. So this is the post order traversal. Okay, and another identification of the post order is root node will come at the last position. Pre-order, root node will come at the first position. So you can also validate some option by this way. Okay, and then mark this answer. Okay, so you can try to solve this because we have less time. Which of the following statement is true about the complexity of a given function where n is the number of nodes? Very based on question to implementation. Oh, This depends on the previous question. Okay, so it is asking about the traversal complexity. Okay, so what traversal we have done in the previous steps. So what would be the complexity if our uh, tree is balanced or not balanced? Okay, so this type of condition is asking. So complexities of big O and log n whether the tree is balanced or unbalanced. So just tell me what is the complexity for this function in the previous question, traversal operation.
Order of login.
So log in.
Order of
How log n?
and log n.
This is actually order of n time, because what we are doing, we are traversing each node at a one time. Okay, and we have only these three steps for each. So this is order of n time complexity, and it doesn't matter what type of tree is there. We are traversing all nodes by this traversal algorithm. So that algorithm will work in the same way that if tree is balanced or not balanced. So that traversal complexity is will not affect by the tree nature, but your searching definitely affect. So if our tree is balanced, binary search tree is balanced, then you will get a log n time for searching. Okay, and but traversal operation is traversing each node, so that will traverse n nodes, so order of n time is required for that. Okay, so that for next question, that one option is there. uh, yeah, C option, order of n whether the tree is balanced or unbalanced. Okay, so this is the answer for this. Next is so this is also related to some properties. Just validate that which option is correct. Consider a binary search tree of height h. Which of the following statement is are true? Okay, so this type of question, one thing we have missed actually, we have not mentioned the base case. So because in different books, some books consider that that height with one node, okay, one node is either zero. But some book also consider that height of one node is one actually. Okay, so both are the possibility for the height calculation in this. If h height is there, so what are the number of elements is there? So accordingly we can adjust our formula. So now I think this question is in the initial terms, so we missed that base case condition. Because of that, some different answer is also possible if anyone consider this as a base case or someone consider this as a base case. So after that, we follow this, we mention the condition. Okay, so what we are actually taking as a base case. So we also mention that empty tree height is zero. Okay, so empty tree means there is no node, height is zero. If one node, height is one, then you can just validate your formula accordingly. Okay, so the number of elements, height is h. The number of element in the tree is at most h. Is this correct?
No, sir.
No, sir.
So this is at most. Okay, so this is not possible because uh, h node we only get like this structure. Okay, so suppose we are getting all the elements in this way. Okay, and here if we are considering the height, one node is one, so that means 1 2 3 4 5. So h equal to 5 here, and n is also equal to 5, both equal to h. But this is not a at most, because our tree may also be a complete or full tree. Okay, like this, where each childs are filled. Okay, so that is also a possibility. For that h height, you will get a 2 to the power h minus 1 divided by 5, 32 or minus 1, 31 nodes. Okay, So this is not true, but at least H. This is true.
Correct, sir.
Okay. The number of element in the tree is at least H. So this is also not
False.
correct because we have got this. The number of elements in a tree is at most. So as we have mentioned this formula, so this is true. Okay. The number of element in the tree is at most. This is wrong. And in a binary search tree, if the number of nodes with zero childs node are n0. Okay, so this is also one observation. So zero child, what is the meaning of zero child and one child? All these things. So suppose we are creating this tree. Okay, so zero number of nodes with zero childs. So that nodes are actually a leaf node. So we are representing that n node. So all these nodes are coming at that leaf node. So for this tree, we can consider that n0 equal to 4. Okay, and number of nodes with two child. Okay, that are n2. So we have the category n2. That means nodes with two child. So you can see 1, 2, 3 are 3. Okay, for this tree. Then n0 equal to n2 plus 1. So this is always true. This we can validate by some observation. So n0 equal to n2 plus 1. Okay. So how we can actually prove this? So let's discuss this. Hmm. So also we can consider the edge actually. If we have binary search tree with n nodes. Okay, so let's explore more. Like this. Okay. So we have three type of nodes in this, n1, n2. Okay, n0 are the nodes, number of nodes with zero child, and 1 are the number of nodes with one child, and n2 are the number of nodes with two childs. I think this is clear how we are getting this three category, and this is the possible only because this is a binary. Okay, so now we have total number of nodes are n, correct? We are considering that we have total number of nodes are n. Okay, so how many edge will be there? Total number of edge will be there. So first condition we can write like this: n equal to n0 plus n1 plus n2. This is correct.
Yes, sir.
Total number of nodes equal to number of nodes with zero child, number of nodes with one child, number of nodes with two child. So this is the one equation we have. And another equation we have, so like how many edge will be there? We can just use the edge term here. So if number of nodes n, because this is a tree, number of edge will be
n minus 1.
n minus 1, correct? Now this number of edge we can also check from these nodes. Nodes with zero child. So how many edge are connected below that? So nodes with have zero child. Any edge is connected below this? No. These category, there is no edge connected below this. Okay. So that means this will not come, okay, in the edge, because we are just making this as equivalent. So n minus 1 we have total edge, but we can also find out the edge with this. So number of nodes with one child. So like this type of, this is the one child, okay, and this is the one child. So how many edge they will? So this node have like as a n1 category. Okay, this node also have a n1 category. So one child means one edge is connected with this. Okay, this one edge is connected. So we can directly write the number of nodes are also representing the number of edge here, one. Okay, into one. So that means this number of nodes which have one child, that means one edge is connected below that. Okay, and plus the number of nodes with two child. So like this category. Okay, so how many number of nodes with two child? This one, like this n1, sorry, n2 category. This is also n2 category, two nodes. So you can see How many edges are connected with each node? 2. And similarly for this, 2. So we can write like this. So we have two nodes with two child. So total number of edges, how much are there? 4. Okay, so 2 into 2. So we can write like 2 into and 2. So this equation is also correct. This is in the form of edge. But we have written this in the same terms n. Okay, total number of edge equal to n minus 1 equal to number of nodes with one child is contributing n1 edge. Number of nodes with two child are contributing 2 into n2 edge. So two equation we got. So this n minus 1 equal to n1 plus 2 n2, like this. Okay, now we can just move this minus 1 here. So n equal to n1 plus 2 n2 plus 1. Okay, so now this is also n, this is also n. So we can make both equivalent. So like n0 plus n1 plus n2 equal to n1 plus 2 n2 plus 1. Okay, so now this cut. Okay, so we will just move this and this here and this part here. Okay, so 2 and 2 minus n2, so this will become n2 and this will reach here. So that is mm, 2 0, yeah, equal to something is wrong.
Sir, n2 plus 1, na? 1 is also there.
Okay, yeah. So n0 equal to this, and n2 will reach here. So yeah, that correct. Yeah, okay. So this actually we are trying to prove. So that means number of leaf node will always be one more than number of nodes with two child. Okay, so this is the true condition in the every node. So if you just observe by any tree, so you will get this structures. Okay, so you can observe any tree like this. Like this. Okay, so how many nodes we have with the two child? So one, this one, two, three. Okay, three nodes. And how many leaf node we have? 1 2 3 4. So you can see n0 is always n2 plus 1. So this is 3 plus 1 4. So this condition is always true. So last option is also true on that. So F is also correct. Okay, so this was correct, and this one and this one. Okay, so let's move to the next. So this was B, D, and F.
Sir,
B,
can
D, F,
you
B, D, F.
repeat the option once more?
Okay, 1 second. So height, which option you are asking?
B1, sir. Sir, I thought
B1. Okay,
sir, D for Delhi.
this one. Okay. So this one. So as I mentioned that this question, the base condition is not mentioned, but we are assuming that if any tree has empty node, means empty, so we are taking h equal to 0 height for this. If any tree have one, we are taking h equal to 1 height. Okay, so that means this is a 1 height. Now you can simply observe the formula. So just create a one tree for the maximum number of nodes. So suppose this is the maximum. Okay, so for height, how we calculate the height? We select what from root node to all any leaf node which have the higher length actually. So here each node, suppose if I connect one more node here, so in this case check root to leaf, which path is the longest path. So this path is the longest path, and in this what number of nodes are coming, so that will become a h equal to 4. So height for this node is actually 4. But we are looking for h height, the maximum number of nodes. So h height, suppose h equal to we are taking 3. So for 3, if we make full tree, Full means no node is missing for this height h3. So this is the condition. So for this we are getting 7 nodes. So for 3 we are getting 7 nodes. So that we can get like this. So 2 to the power 3 minus 1. Okay, so 8 minus 1, 7. So 2 to the power h minus 1. This way we are getting.
Got it, sir. Sir,
Hmm.
like how we define depth and like difference between depth and height of a tree.
So both are the similar terms. So height, so depth is also similar. So we are just looking from the root node what is the maximum depth we are here. So depth is the different representation. So we can also ask for the what is the depth for this node. But height is calculated for the overall tree. Depth can be asked for any node. So we suppose this node, what is the depth for this? So we will just find out root to this path and how many nodes are coming. So 3. Okay, depth for this nodes, if we are considering that this is a 1, so this node depth is a 3. So depth can be checked for any node from the root. But height is overall actually. So consider for the overall tree.
Yes, sir.
Okay.
Understood. Thank you, sir.
So this is done. And next. Okay, so for an activity, we have this starting time is given, end time is given. The following starting and end time activity is mentioned in the chronological order. What is the minimum number of rooms required? So this is also greedy related algorithm. But to solve this, you can simply just write like this. Mention. So first room you are assigning. So that A. Okay. So first room you are assigning AS. AS means started and activity AE means activity is finished at this point. So now one room is allocated for AS. Second is coming because this is already AS is still running. So we have to assign the another room. So like we can like this R1, R2 we have to assign because this activity is started. Okay. CS still both are running. So we have to assign R3 like CS. But now activity A is finished. Okay, so that means this is finished at this level. So room 1 is free. So now next activity will come in the same room R1. So this DS will be assigned. Now CE. Okay, so C is finished. So this is now finished. Now this room is available. And ES is will be assigned here. Okay, so BE. So BE is finished. This one is finished. So FS will be assigned here. But still all three are now running. Now DE, so DE is finished. Okay, GS will be assigned in the same room. EE, so this is finished. HS will be assigned here. FE will finish, GE will finish, and HG will finish. So you can see in this process, if we follow this, we need maximum 0 in this process. So answer for this is 3 room is required maximum. So you can in exam you can solve like this.
So here is minimum now.
Minimum number of rooms we are looking. Okay, minimum number of room is required 3 for the complete process. Okay. Okay, so this is Huffman code. Oh, what happened? Hmm. So same thing. I think you can solve this. What uh, we'll get? So what are the smallest one? 16 and 11. So write like 16 and 11. I'm just writing as a full decimal. So 11. Okay, so this will become 27. And next will be select 21 and 22. So both will be select 21 and 22.
So
So
why are you selecting two column?
which column?
16 and 11.
Because these are the smallest, no? Two smallest. Huffman code algorithm, we always start with the two smallest frequency and generate the tree. So at the first time we have available 5. Out of these five, two smallest one is 16 and 11. So we mention here as like C and E. Okay, and we combine this, so 27 is now also included in this. So we, at the first step we have combined this, but both will replace by now 27. Now we have the frequency available 22, 21, 27, and 30. So out of these four, which one are the smallest one? So 27 is already in tree, but these are not added right now. So we will separate this from the as a separate tree. So 21, 22, 43. This is now combined. Okay, so this become a 43. Now 43, 27, and 30. Which one is the two smallest? So this 30 and 27. So 27 is already there. So we will just make as a node 30. So this is for D. Now this will combine. Okay, so this is become 57. So 57 and 43 are only remaining. So both will combine 100. 100. So now this become a tree, and this 21 was for B, and this A was for this one, 21B and 22 for A. So now just to find out the Huffman codes for this, so that 0, 0, 0, 1, 1, 1, 0, 1. So for A is 1 1, B is 1 0. Just root to this leaf path. What value are coming? And C is 0 0 0, and D is 0 1, and E is 0 0 1. Yeah, someone raised the hand. Disa, yeah. Yes, Disa. Okay. So how many? So we have this message A B C D E. So just add all bits. So 2 plus 2 4 plus 2 6 plus 3 9 plus 8 12. Total 12 bits are required for this message A B C D E. Okay. Yeah, Disa, do you have any question? You raise the hand. Okay. Nobody raised it. Okay. So as I mentioned that this question is we have done for AVL tree this type of question, but now this is for binary search tree. So the element at maximum depth are, okay. So maximum depth means low, which elements are coming at the as a
Sir,
leaf
you are
node.
not audible.
Sorry.
Sir, could you please repeat last step again for previous question?
Oh, that is deleted now. So last step is just a coding allocation. So what of we are getting? Suppose Huffman codes we are getting. Uh,
100.
that 100, that was the top one, but we are getting this type of structure, like, okay, like this type of structure. So how we just mark for the code actually? So we all left edge actually mark 0 value, or right edge we marked 1 value, and 0, like this. Okay, to calculating the Huffman codes, we visit from root node to leaf node, because leaf node is representing the character. So suppose this is A. Okay, so what will be the code for this? Will be, we will traverse from root to this A leaf node. So what value are coming on the edge? So that is coming 0 0 in this path. So that will become a Huffman code. So in this way we will calculate for a Huffman code for each. Suppose this is B, so root to B path is 0 1. This will become 0 1. So we will calculate the total Huffman code length for this. So this is representing 2 bits is required for A. Okay, 2 bits is required for this. Now this is the message. So we will replace each character by this code, and we will count how many bits are there. So that is now 12 answer we got for this.
Okay, sir.
So this is again binary search tree. So binary search tree, here no rotation is required. So only binary search tree is there. 50 is the first node. 80 is the greater than 50. So 80 will add here. 20 is smaller than 20 will is smaller than, so this set connected. 60 is greater than 50 but smaller than 80, so 60 will add here. 10, so 10 is the smallest, 50, is smaller than 50, smaller than 20, 10 will add here. 45 is smaller than 50 but greater than 20, so 45 add here. 65 smaller than 50 is smaller than 80, greater than 60, so 65 will add here. 30 is greater than 50, smaller than 50, greater than 20, smaller than 45, so 30 will add here. And 90 greater than 50, greater than 80, 90. Okay, so which nodes are at the maximum depth? So you can see depth we check from the root node, so these nodes actually, this is coming as at the maximum depth. So what is that for 3? So this is 4, same for 65. So 30 and 65 have the maximum depth for this.
Okay, sir.
So this is property related things. So AVL tree is also a binary search tree, so that formula is also applicable. Okay, maximum number of nodes. uh, but minimum number of nodes in the AVL tree, because AVL is a balanced tree, so that we calculate by this formula. So this formula is very important for the AVL tree questions, just remember this. uh, to calculate the minimum number of nodes for height h, so that we calculate this formula, sh equal to sh plus sh1, sorry, sh minus 1 plus sh minus 2. Okay, so this is wrong, this should be a plus. Okay, and this is the base condition. So we take 0 height means 0 nodes, 1 height 1 nodes, but after that we will calculate s2 like this, s1 plus s0 plus 1. This is the correct formula to find out the minimum number of nodes. So what is the s0 value is 0, 1 is 1 and plus 1, so that will become a 2. So for height 2, minimum number of nodes will be 2. If you want to calculate the s3, so you have to add this 2, s2 plus s1 plus 1. So s2 is 2, s1 is 1 plus 1, total 4. So for height 3, minimum number of nodes will be 4. So just remember this formula, this is important. Okay, so this is wrong because this is minus mentioned. The AVL tree, the absolute distance between the height of a left subtree and height of a right subtree of any node can't be more than 1. Yeah, this is correct. Okay, so this is the balance factor formula. The complexity of searching in AVL tree is log n. This is also correct because we maintain the balance tree. So after balancing, so we will get a log n time. If the height of AVL tree is h, the maximum number of nodes will be 2h minus 1. So this is also correct. Okay, we have already seen this in the previous question. So the complexity of both insertion and deletion in AVL tree is order of n. So this is not correct because our tree is balanced. Okay, so only rotation is required. So in that case, log n time is required for that insertion and deletion also. So this is not correct. Okay, this one, these three answers are correct. Okay. Okay, again, this is the AVL tree. Leaf nodes are there. So we can quickly create 8. Okay, now 8, 4. Okay, so 0, 1. Now 8, 4, 1. So like 0, 1, 2. And this will rotate now. So 4 and 8 and then 1. Okay, this will become rotate after 3. So 3 will be insert here. Okay, so 0, 1, 1, sorry, 0, and this is 1, 2 minus 1, 1. Now 9, so 9 will add on this side. 1, 3, 3, 8. So 9 is greater than 4 and 8, so 9 will be add here. So again still 0, 0, 1, 1, 0. Okay, then 2. So 2 will insert 4, 1, 8, 9, and this is greater than 2 is greater than 1, but smaller than 3. So now this is the situation. 0 1 2, okay, and 0 1, and this is 3 minus 2 1. This part is now right left. Okay, so this will rotate 2 times, so this will become like 4. This will rotate first, so 1, then 2, and then 3, and 8 and 9. Now this will rotate anti-clockwise, so this will become like 4, 2, 1, 3, 8, 9. Next is 11. 11 will add here. Okay, and then this part will be rotate one time. So finally we will get like this: 4, 2, 1, 3, and 9, 8, and 11. So now this become a balanced tree. So 1, 3, 8, 11 are actually, this one is the correct answer on the leaf node. Okay, so we have also seen this property. So here codes are given. Which one is not the correct one actually? Not possible valid codes. Which of the followings are possible valid code? We are asking. So here you can check the, because we have 1, 2, 3, 4, 5, 6. Hmm. So one validation you can check prefix code. Okay. So in the codes, just check smaller code that are coming as a prefix or not. So that validation you can do. So like 1 1 is coming at as a first, no. Okay. But you can see 0 1. The 0 1 code is coming as a prefix in this. So this is a invalid code. Okay. Same 0 0 0 1 0 1 1. So 1 1 is not coming at any place. 1 0, no. 0 1 also not, and this is also not coming. So this is a valid one. And here 1 0 1. Okay, so you can see this is coming as a prefix. This is also not valid. So 0 0 not coming as a prefix. 1 0 1 0 is also not coming. So this is also valid. Okay, so prefix property you can check as a one thing, and also one thing you can check, like we have total 6 characters. Okay, so the possibility is one node will connect like this. After that each node is connected like this. Okay, so this is the maximum length of the code possible. So 1 2 3 4, and total we have 6. So 1 2 3 4 5, and one more. Okay, so in this case the maximum length is possible 1 2 3 4 5. Okay, so 5 length code is possible maximum. So suppose if any code has 6 length, that is not possible. Okay, so suppose if in any code, suppose in this example like this is given 6 times, so that height is that number, bit length is not possible for the bits. That is also one check. Okay, so this is straightforward question. We have seen this in the meeting, week 7. So the maximum number of meetings that can be held in the meeting room. One here we have the one room only. Sorry, we have only one room, and we want to perform a maximum number of meetings. So anyone can tell me how we solve this?
Check the end time.
Check the end time, and how we will pick?
Sort
Uh,
the time.
by doing lateness.
No, here this is not a lateness.
First,
This is
we will
start time,
sort
end
them
time.
as
List based on.
we will sort the end time first.
after
Huh.
that.
So this can be solved. The first step is sort the activity or meetings based on the end time. Okay. So like this is the three is the smallest one. Yeah. So this will perform first. After that, so one, and next is this two, and three, four, five, six. Oh, we missed it. 1 second. So this is the one, and this is two, three, and four, then five, then six, then seven, 8, 9, 10, 11. So this order we should follow actually. After that, we can simply check. So if this activity, if we are starting, so this activity is starting from 2 and will end 3. So 2 to 3, this is running. And next activity we will pick, which is coming at 3 or after this. Okay, so second activity we are picking, so this is starting at 3, so we can pick this also. So that will perform till 5. Okay, so this is also selected, this and also selected. Now 5 is the ending time. Next activity will check with this end time, so that is this one. So 4, you can see previous activity start completing at 5 and it is starting at 4, so this is not possible. So we will ignore this. Okay, so next fourth one is this one. So this is again starting at 2, so that is also not possible because our end time is done 5. So fifth one is starting 6. Yeah, that is possible. Okay, because it is starting. So one gap is there, but 6 to 8. Now this is done. Then next sixth one is start coming at 7. So this is not possible because this is smaller than end time of previous selected. And next is this 6 9. So 6 9 again we cannot select. 8, this one. Yeah, this we can select. Okay, so this 10 to 11. And next is this one 11 to 12, so that is also possible. And 10, this is not possible. Okay, because it's starting at 9, so that is not possible. And then 10 and 11, so 13. Yeah, this is also possible. 15. So how many activity we have done? So 1, and then 2, then 3, and then 4, and then 5, and then 6. So 6 activity we can perform in one row maximum. Okay. So we have already done this. So 15 for the mock. So what are the maximum? 15 into 14 divided by 2.
105.
7. 105.
Yes, sir.
Okay, so this is already done in the mock. Okay, so this is related to the complexity in week 8 we have discussed. Which of the following statement is true? Using MOM, the worst case running time for find kth largest will be order of n. Is this true? If you remember, MOM, that fast select, quick select, these algorithms. So that actually, so in the partition we follow the we follow the quick sort approach in that. So we first find out the pivot element and we fix at the pivot position, and after that we ignore the one half and select only the one half. But still, partition process take order of n time. Okay, and if we are using MOM, so definitely this will our pivot element will come in between at some place, not on the corner. So so if you remember this, what was the recurrence relation for that is, so Tn equal to Tn equal to Tn by 2 plus 1. Sorry, n. This was the recurrence relation for quick select using MOM. Okay, so if you calculate the complexity for this recurrence relation, so this will reduce actually. So first step n, next step n by 2, like this. So that next step n by 4. So if this order is reducing in the your tree, so we will directly select fn as a complexity. So this order of n. Okay, so this is true. Using MOM, the worst case running time to find kth largest will be n log n. So this is not correct for uh, finding kth largest. This is true for the quick sort algorithm. So that is one. Okay, improvement of the quick sort algorithm. Using MOM, the worst case running time for quick sort algorithm become order of n log n. Yeah, this is the correct one. Okay, so 1 and 3. This is the correct option. Okay, number of inversion. So that is the simple one. So we can check 1, 4, 3, 6, 2, 5. So 1 is not making any inversion with any road. So 4 is making with 4, 3,
Two
4, 2.
inversions.
Okay, 2 inversion. 2 is value are smaller. 3 is making with only 3 and 2. 6 is making 6 with 2 and 6 with 5. And 2 is not making, 5 is not making. So these number of inversions are there, 5. Okay. So this is the, again this is a complexity based. So we have seen this complexity. Mhm. So you can calculate what type of complexity we have seen. Maybe some is so you can see this. You can remember this recurrence relation. This is for binary search, if you remember. So we just reduce half of the part at every time, or and we are only checking the middle element comparing. So that is the constant space. So this is actually a time, log n time operation. So that definitely this will match with the log n. And if you remember this, so this is a equivalent condition like so tn. This step n is are the step after 4 calls are there. So with n by 4, n by 4 each. And if you will add all these, so 4 into n by 4. Okay, so again n.
N
Next level
square.
n by 16, n by 16, 16 times. So 16 into n by 16. Again n. So in this case, our total number of steps at each levels are same, equal. So we calculate the complexity for fn log n. So fn value is n, so that is log n. So that is the way to if our steps are same at the each level. So that is now n log n. This one. This is the okay. So what about this one? So let me calculate this also. So t n and n. Then now two calls are there n by 8 and n by 8. So that means 2 into n by 8. So you can see this is now reducing n by 4. First was n by n, second level n by 4. So if you follow this, this will all reduce again. So in the reduced case, we only pick the fn as a complexity. Okay, so what is the fn? So that means order of n. This will be considered as a complexity for this. So this is now matching with this. The remaining part, this is the n minus 1. Okay, so n time. Hmm. So this is your similar of your selections or insertions or type of things. At first step, we are processing an element, then one element is shifted at the correct position, then n minus one element like this. So you will get a series of like this n steps, then n minus one step, then n minus two steps. So that will become a order n into n plus 1 by 2 like this. So n square. Okay, so this is matching with this n square. So this is the combination. Okay. Now remaining questions are also related to this. So we have discussed this just now for quick select. Okay. So n by 2 n and every time our complexity will reduce. So we will get a order of n time for this. This we have already done. So next is 2t n by 2 plus n. So this is, if you remember that, this is the recurrence relation for merge sort, or best case or average case of a quick sort. So complexity for this will be, or
N
n
log.
log l log n, this one. Okay. And what about this? So this is the increasing case. Okay, so tn, now this become a 4 call, each as n by 2. So here this was n, but this time if you add this, you will get a 2n. Okay, so 4 into n by 2, 2n. So in this way again, it will divide 4 times. So n by 4 at each, and 16 time. 4 into 4, 16. 16 into n by 4. So this become a 2 to the power square n. Now this is increasing. So in that case, we select that fn value, this is n, and log cr. Okay, so c value is this divide value, so that n log base 2, and r value is this one. Okay, so 5 to the power 2 we can write. So that will become a n square. Order of n square is the complexity for this. Oh, all done. Okay, so this was the last question. So similar type of questions will be there. So we have done. So any query, if you have, you can ask. Any query, anyone?
Yes, sir. Huffman coding. Sir, can you revise?
Okay. So I am just taking random example. So suppose we have 6 character A, B, C, D, E, F. Okay, and frequency are given. So frequency sometime given in the probability or something, sometime direct value. So suppose I am taking 10, 5, 30, 20, 15, and 8, like this. Okay, random frequency. How we will create a Huffman tree first, and then how we will generate the Huffman codes. So for Huffman code, Huffman tree algorithm, this is a greedy approach. We always select the frequency, two smallest frequency, okay, which are remaining from the remaining frequency. And if we are picking the character frequency, that we will make as a leaf node, and we will start creation the tree in the bottom up manner. So what are the two smallest one? 5 and 8, correct? So we will start from 5 with the 5 and 8, 5 and 8. Also you can mention the character. So C is this one and F this one. So combine this 5 and 8, 13. So now frequency are remaining. This is the 10, this is 30, and this C and this will replace by 20 and this 15. Now 13 will also consider in the category. So I am just marking this. This is a node frequency, which is already in the tree. So again, we will select two smallest. So which one are the two smallest now? 10 and 13. So 13 is already in the tree. We will just consider this 10 with this 10. Okay. So 13 and 10 are 23. So now this is also done. So 30, 20, 15, and we have this 23 now. Okay. So which one is the two smallest now? This one.
Okay, yes.
Okay. So these are the character frequency actually. So this will create separately. So you can make this as a separate from here. Uh, 20 and 15. So 15 and 20, and both will combine like this. 35. Okay. So this is now become 35 and 30. So only this is remaining. So which one? Okay. So 35. So 35 is already there. 30 we will pick. So 30 just put with this. Now this becomes 65. And now only 65 and 23 is remaining, so this will combine finally. Okay, like I say 88. So leaf 15 was the frequency of E, and 20 was the frequency of D, 30 was the frequency of B, and 10 was the A. Okay. So now we got this Huffman tree. Okay. Now just mark edge weight, edge level actually. On left edge 0, all left edge 0, all right edge 1. Hmm. Now just how Huffman code will generate. So A, B, C, D, E, F. Okay. So just traverse from root to that node, character node. What that bits are coming on the edge. So for A is at this place. Okay. So to create to this 10, in this path, 0 is coming first, then 1.
Yes.
0 and 1. For B is the 1 1 1 1. Okay. For C is at this level, so 0 0 0. So 0 0 0. And for D, this is 1 0 1 1 0 1. E is the this one. Okay, so 1 0 0. F is 0 0 1. This one. This is called as a Huffman codes. Okay, so you can count 2 bits,
Can you
3
take one
bits,
example on
3
probability,
bits.
sir?
Probability is the same thing. So these values, suppose if it suppose we are considering that we have the 100 actually character, and the probability is given like point 2 5 for one character. Same thing you will do, like point to 10 is the
Okay,
things.
okay. Then we
So
find
just
number of frequency.
so just pick the smallest probability value first and do the same thing.
Okay, sir.
Hmm. Okay. Yeah. Any query? Other query?
No, sir.
Okay.
Sir, one
Okay.
more
So,
session, right?
हाँ Vivek बोल. Yeah.
One more session tomorrow.
No, no. This I think that is TS session. I am not sure. Tomorrow, Saturday, na tomorrow.
Yes, sir.
So TS session will be there on that schedule.
Okay, sir.
Okay. So if there is no query, then we can close the session. Yeah. Thanks everyone.
Thank you, sir. Good night, sir.
Thank you, sir.
Thank you, sir.
Thanks.